Hello everyone. So we will have some remarks on linear algebra, and so this is the first video I'm making. So okay, there were a lot of other practices, but this is the first one that I will probably release. So we want to consider this question that if given a matrix that B, which is n by n, so let's say B n by n. So it's a matrix basically in Mn over a field F. Okay, so if we have this matrix and we have some vector x is a vector which is n times 1 f, which is non-zero and it's in the kernel of B, then the determinant of B is equal to 0. Okay, I mentioned this as a fact, and I want to explain because many of you asked me why this holds. But to actually explain this, we instead prove something bigger. So if the determinant of B is equal to 0, you agree that the columns of B are linearly dependent. So you should think of determinant as signed volume. For example, if you have these three vectors, so you have the volume of the parallelepiped that actually is generated by them. And this volume with some orientation, so it matters for the determinant that which order we consider this three vectors, but for the determinant for the volume it doesn't matter. So if you look at it this way, for example, if the determinant is 0, means that this three vectors don't generate any volume, don't generate a parallelepiped, then they have to be like in the same plane, and so the determinant is 0. And determinant of the columns of this matrix, if you will. So if B is given by B1, Bn, so this line is same. So this is linearly independent. So, and you can see also that the determinant is 0 if linearly independent. We discussed this before. Another thing is that if, so we want to say if the columns of B are linearly dependent, if and only if Bx equal to 0 for non-zero. Okay, let's discuss this. So B is given by a matrix. So B is this matrix that has columns B1 till Bn. Okay. And I want to consider x1, xn. If I want to multiply this, so if I write bx equal to this one. So I claim that this is a vector given by x1 times b1, etc. So xn bn. Okay, so maybe you pause the video, and then you see why this is true, and I explain in a second. Okay, so why this is true? Because b1 times bn, if this is a matrix, and if you multiply it to 1, 0, 0, just gives you b1, this first column, right? We understood this because, for example, if you are happy, just do an example. 4, 5, 6 times 3 times 2. This I have to multiply it to 2 times 1. Okay, so let's say 1, 2. This gives me 1, 3, 5. So it gives me the first column. Okay. So if I multiply the same matrix B, Bn, this with times x1, 0, 0, would give us x1 times b1, right? We all agree. And similarly, if we multiply b1, bn to 0, xn, this gives us xn, bn, okay? So therefore, we have this equation that we wanted. So let's put a star, this equation that we wanted. Okay, so we have that. What does it mean though? So we are multiplying b to x1 till xn. We have got some linear combinations of the columns of b1 till bn. Okay, and so if bx, so yeah, let me write here. So another color. So if bx is equal to 0 for non-zero vector x, then this is equal to 0, this is equal to 0 vector, right? This is equal to 0, this is equal to 0. And this means that, of course, b1, bn, which are the columns of b, are linearly dependent, because we found non-zero coefficients which make b1, bn, the linear combination, equal to 0 vector. Okay, so what else do we want to prove? So we also prove this. So if bx is equal to 0, the columns are independent, or if the columns are independent, so we put this coefficients that we get. If they are dependent, we put these coefficients in this column vectors, right? And then we write this matrix b1, bn, and this would become 0 because these are equal. Okay, so we have proved both sides. And so if bx is equal to 0, then if and only if b is not invertible. So if b is not invertible, you also have seen in basically linear algebra part 1 that this is equal to 0. Just it's a good time that you go over your notes and look how actually you've seen this, how it was proved for you. Okay, so b is not invertible. So but let's make a remark on this one, which is very easy. So I want to say that if b is invertible, then bx equal to 0 implies that x is equal to 0. That's very easy. So I just multiply both sides to b minus 1 bx equal to 0. So b minus 1. And this is x, right? Because b times, and this is equal to 0. So therefore x is equal to 0. Okay, so this means that therefore this if x non-zero in the kernel and bx equal to 0, therefore So that's what they have proved. B is not invertible. Okay, so what else have we left to prove? If B is non-invertible, and if B is not invertible, that there is an element in the kernel. So, well, we can also say, we can go through this way. So if B is not invertible, determinant is equal to 0, so the columns are linearly dependent, and then say that, okay, there is one element in the kernel of B. Okay, so we have actually proved every relation between this. Okay, talk to you in the next